Hello and welcome back to my channel. So this is part of the upper intermediate series. Congratulations if you have completed the beginner and intermediate series already. If not, please check out the playlist below and please also like, share and subscribe so I know to make more. Okay, let's get to it. So today we're going to talk a bit about linear search and we're also going to talk a little bit about the big O notation. So linear search. Let me get my playing cards. This is basically what linear search is. It's some stack of something, let's say in a program where you have in enterprise, it could be like your social security number. So in like the workplace, it could be something like a program running to find someone else's social security number, or it could be a bank account, or it could be anything like that. So let's say, for instance, linear search, what it does is, let's say I want to find this card in this deck, but pretend these are files or something. So what linear search does is it takes up each individual and goes, no, that's not it. Check, no, that's not it either. Check, no, that's not it either. And it goes through it like that. It's super inefficient. It's super inefficient for us as humans too, until it gets all the way through these cards until you get to your actual number, let's say, for instance. That's just an example. So what we want to do with linear search, and the reason why we do it, is because it's easy to program, test and debug. So it's usually for smaller sized things like arrays or things like that. So you're looking for a search key. The search key is the term, but actually it could be, usually it's a number or someone's name, or it depends on the type of array that you're looking for through a whole bunch of data. So usually with an array, you have all your little boxes with all your values in it, and you go through each individual one. And that's your linear search. So then we have binary search, which I'll do in the next video, which is more efficient, but it's harder to implement. So for now, we're just going to look at linear search. Linear search implements one of the worst case algorithms because it's so inefficient, and there are 3 different types of big O notations. And the reason why we use big O notation is so that we can differentiate between one algorithm and another algorithm to see whether the speed, basically. It also impacts performance, and that's now looking at your hardware connecting to your software as well to see how powerful it is. Also to do with how the program is implemented, and all these factor in and play a role in determining how quickly your program will run. So we have 3 different types of big O notation. This is what I'm covering so far. If you want more detail, please go ahead and look it up, but we're just introducing the topic now, so we're going to stay with this. So we have the first, which is known as order 1, or you have like basically a big O and then brackets and 1 in it, and that's called order 1. Then we have order n, where the array can increase in size, and that will also increment all the time. So we also have O squared, okay, so that's another type. Order n squared is another type, but we'll come to that at the end of this video. For now, we're going to have a look at this program. So we have our class here. As usual, we have our imports before a class. All of this was covered previously, so I hope you're on track with me so far. The layout of the program is important. Imports, because we're importing the packages with all the classes that we need. The class that we're creating, and we've called it with a capital letter because it's Java as well, linear search test. I have a method, it's a static method because it's called within the static void main, and I call it linear search. It's also static and because there's one of it. So int data, so it takes a data array and it takes a search key. Now I've just called it search key, but you can call it whatever you want. You can call it number or input number, but the official term that we're going to use throughout this and throughout all the search things is search key. So we loop through the array. We're going to use a for loop, and we're going to use count here. I've got count written in, but actually we're going to refer to the index of it. So more appropriately would be to call it index. So I'm going to do a refactor here and rename it to index. And as you can see, once I type it in, all counts then change to index. And so if you're unsure about arrays, please go back and check the array video. We have an array and each index in the array, and then we have the values of the array. So we have the index versus the length, okay? They're two different things. So index always starts at 0, but the length of the array can be 10, from 1 to 10 elements in the array, but it starts at 0 to 9. So that's why we have our less than the length. So we have our index is equal to 0, index is less than data, which is the array that we take in, dot length, and then we iterate through it. We put index into the data, and then we see if it equals the search key. If it does, we return the index, and if it doesn't, then we return -1. And this is going to be called down here, and because I've highlighted it here, you can see that it's called here, but I'll go through this part of the code first, which is pretty straightforward. This part of the code is our usual input from our user, our scanner input, and then we have our secure random gen rand numbers. You can call it whatever you want as well. I just decided I'd call it generate random numbers, gen rand numbers, so it's easy for me to see. We create a new array. I'm going to comment this. Ooh, new array, and with this then you can see the length of the array is 10. So this is where the difference, the array is 10. You can see here that I ran the code already. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But the index and how we access the values within the array is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So how we access the information within the array, it's the same notation, just so you're aware. We could have also done an iterator list array, and I could have put in numbers in this, but we're going to use the secure random instead. And it's going to go as far as 10 plus 90. So then we have our toString. We use, of course, here when I look up our arrays, which when I click on it, it should show up here. This class contains various methods of manipulating arrays, blah, 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 blah. It's part of the collections, and that's really important because as part of the collections, we have our toString data. Otherwise, I wouldn't be able to print it out. So that is one thing. If you're unsure about collections, please go back and check that out as well. Otherwise, if I just said data here toString, it wouldn't print out. Let's do that actually, because it's an important thing that a lot of people confuse. So if I was just to say data toString, and you can see what happens when this is the data.toString when we generate it. So we're just populating the array here. I'm going to put here populate the array. Here we're going to instruct the user to give me an input, and that input, obviously we already have our scanner up here to take an input, and I just read in the next int and pass it through to an integer variable. And if it's not equal to -1, then I go through and I call my linear search, and this is the only place where it's actually called. So this is where it's going to come back and return into the position the index. So if the index is if the input is equal to -1, then it says not found. So, or if the index is equal to -1, so that's our sequential, not our sequential. this is our -1 is usually the when it finally checks for the index. So we'll go through the code first. Let's run it. You can see, I'm going to check the box, always save. Now you can see here that this is data.toString, so it's no good to us. This is where we have to use collections for printing out the array. So we basically wrap it, and if you're unsure about collections, please go back and check that video as well. So I'm going to take out that line of code next. It's not correct. And let me just run it again. So we have 30, 79, 26, 35, 80, 50, 38, 66, 87, 60. And if I just put in 10, let's say, it's not found. So it gives me I can do another input. So I'm going to say 60. 60 was found at position 9. So it returns the index as we know. So 0, 1, 2, 3, 9. Okay, great. It's at the end of the array. And then if I say -1, it finishes. So with linear search, the reason why it's inefficient is because it doesn't sort the cards. So if I was to sort all of the deck out first, pretend these are all numbers. And for binary search, the reason why it's really efficient is, and I'll cover this more in the next video, is let's say if I wanted the middle number, pretend this is the middle number that I'm searching for, I would check the middle first and then it would just finish. But I'd also check the middle first and see if, let's say if it wasn't the middle, I would check, because it's sorted, all of the previous ones I can put away now, I can throw them out. I can just be like, yeah, that's fine, because they're all less than the number that I need. So when it checks the middle, it checks if everything to the left of the middle is smaller than the number. If it is smaller then forget it. If it's not, then go to that section. So it's more efficient. Now we can go on to binary search. So I'm going to type out some more stuff, and I'll catch you in the next video, and I'll also go through some more of the big O. But for now, this is our linear search, and I want to keep this video short, and thank you so much for subscribing. I'll see you in the next one. Bye.